Hi and welcome along to the diffraction grating. So what we're looking at here is some white light going through a diffraction grating. We'll pan back and have a look at the arrangement in a moment. So we've got a white central maxima, and then symmetrically, well, the one on the left's a bit brighter. We've got a pattern, a full spectrum, blue on the inside through to red at the outside. So let's move back. So what you'll see here is we've got a thing called a diffraction grating. We'll talk a lot more about that. I've got a plastic block that's just acting as a lens and just a slit and another bike light. Okay, what you see here is same diffraction grating, but we've now got the light passing through. It's just a red light from the laser. I'll show you that in a moment, passing through the diffraction grating. So it's much easier to follow what's going on. If I just rotate the diffraction grating, just move that support out of the way, you can see very clearly now, it's very obvious which is the center dot. That's what we call the n equals 0. The first dot out is the n equals 1, and the next dot out is the n equals 2. Right, just looking down on the arrangement, there's the diffraction grating, there's the laser, there's some notes from an earlier video. So we just do a quick wiggle here. You can see that's the n equals 1, n equals 0 spot in the center, n equals 1, n equals 2. It's just falling over because the blue tack isn't holding it very well. And we're going to talk about angles, and the angles are measured from that straight ahead n equals 0 beam from the diffraction grating out to the n equals n and the n equals 2, etc. Okay, so I'm going to try and summarize what you've just seen in the demos, and then we're going to derive the diffraction grating equation, and then you can have a bit of a practice later on at using the equation. So we had our beam of laser light, coherent, well-focused light, hitting the diffraction grating. So you can see the diffraction, there's the screen, the diffraction grating was a great step on from the double slit. The clarity of the patterns, even on the white light, was way better, wasn't it? And on the screen we saw a really well developed set of spots. We call this one, the center one, the 0th order, and then the first and the second, and they have numbers as well. So this is the n equals 0, the n equals 1, and the n equals 2, and those numbers are going to turn out to be important. And I said earlier, you need to understand that we're dealing with angles here. Okay, the angle to the spot. So that angle there, theta, could be to the first, second, third, depends on how many spots there are, but it's always measured from the straight through beam. Here's our diffraction grating. So actually I forgot to talk about that, but ours was 300 lines per millimeter. Well, first of all, just pause and think that's a lot of lines in a millimeter. If I said to you, here's a ruler, measure out 1 millimeter and then chop it up into 300 equal parts, it's a challenge. So they have to be very precisely made. The other thing that I think presents a problem here is in our equation, we're going to need to know d, the distance between slits. And it turns out actually for a lot of students, that's actually the hardest bit of this. So let's just go through that. So what he's telling us is 1 millimeter is divided into 300 parts. So what is d? Well, there's two ways you can work that out. They're both essentially the same. One is to say, well, I want 1 millimeter in meters, which is 10 to the minus 3 meters. Much safer than writing 0.001. And then I'm going to divide that by 300 because I've divided that 1 millimeter into 300 parts. Or similarly, you could say I've divided 1 whole meter, and if there are 1,000 millimeters in a meter, there are this many slits. If we had a whole meter of them, obviously numerically those two things are exactly the same, and we get D. So Now we're going to have a look at how to derive the equation. Mathematically, in terms of the algebraic manipulation required, this is pretty straightforward. What makes this derivation difficult is that you need to be able to draw the diagram and understand the diagram. I don't think once you've got your head round it, it's that difficult, but we just need to spend a moment making sure you've got what's going on. So the first thing I need to draw is the diffraction grating, kind of really zoomed in. Yeah. So each one of these is one of the slits in the diffraction grating. I think I can just add one more. The light's arriving from this side, and then I'm going to draw rays, and these rays are all going to go off and form a bright spot. Now, each one of what actually happens is the light diffracts through here and it spreads out in every direction. But we only get constructive interference in certain allowed directions, and we're going to find the angles of those directions. So I'm just going to say that each one of these parallel lines that I'm drawing is going to go off and form a bright spot. Now, there is a slight approximation here, it's incredibly slight, that these lines are drawn parallel, but we also assume they're going to meet. So let's just pause. Is that a good assumption? Well, that distance there is a 300th of a millimetre. And if these rays meet 1 metre away, that's really not very much convergence at all. So it turns out it's actually a very good approximation. I'm also going to put in a dotted line, and these dotted lines represent the direction to the n equals 0 or the straight ahead ray. And then, as I said, that angle there is theta, going out to the bright spot. So, what do we know about this triangle? Well, we know that because I've just said that distance is d, the distance between adjacent slits, and we know that if this ray and this ray are going to form a bright spot, then the light must be in phase. Okay, so we've got different paths here and we've got in phase. So hopefully you're thinking, right, that probably tells us something about the number of wavelengths path difference, doesn't it? So if I just draw that line perpendicular, so that, because these two lines, the dotted lines are parallels and the black lines are parallel, they've both got to be the angle theta. If I draw a line perpendicular to that ray to hit that slit, then to my mind it's now clear that that short distance there in that little right angle triangle is the path difference, isn't it? This is the extra amount of distance it travelled. Well, if we know that's the extra amount of distance travelled and they're in phase, then that must tell us something about how big that path difference is. And if you think about it, it could be 1 lambda, 2 lambda, 3 lambda, or no lambda, which would be the straight ahead. So this distance here is n lambda. And that n is crucial. That's just what we talked about with the spot. So the centre spot, n is 0, 0 wavelength path distance. The next spot out is n equals 1 wavelength path difference, etc. So we've now constructed a small right angle triangle. That angle there is 90 minus theta. And because the dotted ray is right angles to the grating, that angle there is theta. So we've now got a right angle triangle. What I'm going to do is just run around the edge of the right angle triangle with an orange pen, just so you can see that's the right angle triangle that I'm referring to. And we've now just got a very simple bit of maths to do. In this triangle, you can see that D is the hypotenuse, theta is the angle opposite n lambda. So we can now relate those quantities, can't we? So we can say that sine theta is equal to the opposite, which is n lambda, divided by the adjacent, which is the hypotenuse, which is d. So if we rearrange that, we get n lambda equals d sine theta, and that is our diffraction grating equation.